Hello, BC Calc. This is your day 94 notes. Today we're going to be talking about yet another integration technique called trig substitution. Before we get into what trig substitution looks like, there's a quick warm-up question for you to get started. I'm going to give you a hint right now about this warm-up. If you don't want a hint and you just want to try it on your own, hit pause. If you do want a hint, keep listening, because I think the best approach here to integrate secant to the fourth of 3x and then tan cubed to 3x would be to break secant to the fourth into secant squared times another secant squared. Okay, so once you break it up into those two secant squareds, replace this one with the Pythagorean identity, and then think about a good u substitution that's going to make sense based on what you have left. Okay, so those I hope are some pretty good hints that can help you get started on this one if you were unsure about the best route to go. But think about what we want u to be such that du has something to do with this. Okay, and then you should be in a good place to be able to integrate in that warm-up. Right below the warm-up, you see that we have a quiz tomorrow. Okay, so on the quiz, it's going to be mostly integrals, but within those integrals, you're going to have to know a lot of trig identities. So any of the trig identities that you think are important to reference, make a quick list for yourself down here. I'll show you my list next time we're in class. Hopefully a lot of things match. You let me know if you have anything additional on there that I did not include. Okay, so beyond that, let's go right to the next page. This is going to be generalizing some rules here that I'm hoping we're pretty familiar with. So if you look at that first example, it kind of looks like, right, this is going to be an application of the antiderivative that would represent tan inverse. So what I want to do is, in general, if this is some number that we can represent by a squared, same thing over here for sine inverse, then how can we generalize a pattern that would represent the antiderivative in terms of that value of a? So the first thing I want to do is, if we were going to approach the tan inverse one, is I would take out an a squared from the denominator there. So that would be a squared, if I factor that out, 1 plus x squared over a squared. All right, and since a squared is just a constant, we can move that to the outside. And we know that in order to determine the pattern for tan inverse, we kind of have to write this as some quantity squared. So that hopefully is pretty easy at this point to represent as 1 plus the quantity x over a squared. So a quick u substitution would allow me to determine that if u equals x over a, that du is going to be 1 over a dx. And therefore, if I multiply both sides by a, we would have a balance here. So if I do a times 1 over a squared on the outside, then this becomes du over 1 plus u squared. So we'll notice here that this a cancels with one of those a's, and we get 1 over a on the outside. And then finally from there, we know that this is tan inverse of u, but u is really x over a. So the general pattern here with tan inverse is that if there's a number here that's representative of a squared, if you take the square root of whatever that number is, that's going to go underneath the 1 on the outside, so it's 1 over a. And then the inside is going to be represented by x over a. So if I jump actually right below here to this example, dx over 25 plus x squared, could I do that whole process where I remove the 25, I kind of factor that out, do a u substitution? I could, but if you're somebody who likes kind of remembering and memorizing patterns, the pattern here would be that if a squared is that 25 number, then the value of a is 5. And if I follow the general pattern that we derived here, it would be 1/5 tan inverse of x over 5 plus c. I want to see if you can do a very similar derivation over here. And I'll show you what my derivation looks like next time for sine inverse. But what I'll tell you is, if you work your way down here and do the derivation for sine inverse, see if you can prove in the end that it's sine inverse of x over a plus c. So a pretty similar look to this over here if we have this number a squared underneath. But notice how there's not a 1 over a out front. So that's kind of the key difference between those two generalized patterns. So once you kind of go through your derivation, hopefully you'll find that that matches. And then from here, if I wanted to do this specific example without kind of factoring out a 16 and then removing it from underneath the radical, pulling it to the outside, all that business, if we know that a squared in this example is 16, then we know that a is 4. So this very simply becomes sine inverse of x over 4 plus c. So it's nice to have these additional patterns, but if you are not somebody who wants to memorize them, or if you get stuck on a test and you're like, oh man, I don't remember, is this the one where I do 1 over a out front? Is it not that pattern? You can always default to doing a u sub and doing some algebra to manipulate that to become 1 minus a quantity squared under the radical, and same thing over here, 1 plus some quantity squared. So it's nice if you like the patterns, but of course we have other ways around it if we don't like the patterns. Okay. Next thing we're going to talk about is getting into some trig sub here. So as far as trig substitution goes, we're going to be looking at integrals that have a squared plus x squared in them. Now, that a squared plus x squared isn't necessarily in the denominator because then it's tan inverse. You're going to see some quite different looking integrals if you have something of one of these forms right here. Okay. And the hint is to think of these as part of a Pythagorean triple. So for example, if you have a right triangle where, let's say, this is some angle u, I'm going to define this side to be x and this side to be a. We would have, something that relates x squared and a squared to get the length of the hypotenuse. So the length of the hypotenuse in terms of x and a is radical x squared plus a squared. So the trig function that you're going to use, if you have a setup that looks similar to this with x squared plus a squared in it, is most likely tangent, because tan of the angle u here is going to be opposite over adjacent. And therefore, within the integral, if you're looking to define x somehow, x could be written as a times tan of u. Okay, so you're going to see what that looks like in some examples in just a moment here. All right, similarly, if you wanted to do something with x squared minus a squared, the setup for that would be, if this is angle u right here, I'm going to let the opposite side be x again, but now I'm going to let the hypotenuse be a. So we know that if I were to determine this missing side right here, that this would be represented as the square root of hypotenuse squared minus that opposite squared, so radical a squared minus x squared. And in this case, the trig function that's going to make the most sense to use to define x is sine. So sine is going to be opposite over hypotenuse, and therefore x will equal a times sine of angle u. Okay. So you'll see how these are used in doing some substitutions within an integral, coming up right in our first example here. Okay. So these are kind of cool because they use some identities that we're hopefully pretty familiar with and accustomed to using. But for example, if I give you radical 25 minus x squared and we want to integrate that, first of all, it's not sine inverse, right? Sine inverse would have to be something of the form 1 over that radical. So in order to figure out how we're going to integrate this, when you have the radical involved, it is going to be a trig substitution with sine. Okay. So what I'm going to have you set up is that if that adjacent side to angle u is the square root of 25 minus x squared, how do we then define the hypotenuse on the opposite side to make that true? Well, hopefully you're recognizing that if the hypotenuse is 5 and the opposite is x, then this side that's remaining is the square root of 25 minus x squared. So if I use some right triangle trig with relationship to angle u, I can actually replace that quantity underneath the radical, at least that x quantity, with what it is in terms of sine. So sine of u is going to equal x over 5. And therefore, x is equal to 5 sine u. And since I'm replacing x under the radical with 5 sine u, we're now integrating with respect to u. So therefore, I have to know, well, what's dx equal to? So the dx is going to get replaced with the derivative here, which is 5 cosine u du. Okay. So now that we know what dx is going to get replaced with, now that we know what x is going to get replaced with, let's go back to the integral here. and take the square root of 25 minus x, which is 5 sine u squared. And then our du is now 5 cosine u du. All right, let's see if we have any better luck integrating this with some now trig substitutions involved. Okay, so from here, we know that this is going to turn into 25 minus 25 sine squared underneath the radical times 5 cos u du. All right. If you factor out a 25 and then remove that from the radical, that comes out here as a 5. There's also a 5 over here, so that product is going to be 25 that you can pull all the way to the front. Hopefully that's an okay step to then get 1 minus sine squared underneath here times cosine u du. All right, so now we're kind of at to a kind of a key step here. What is 1 minus sine squared? That should be jumping out to you as a really key identity that we're familiar with. It is cosine squared. And now look at what we have. We have an integral all in terms of the function cosine. In fact, the square root of cos squared is cos, and cos times cos is the integral of cosine squared. Okay, look at where we've come. Okay, we broke this all the way down to the integral of cos squared, which we know how to integrate using that double angle substitution. Cosine squared is 1 plus cosine of 2u all divided by 2. Is that an identity that you wrote on the front of today's notes? Maybe it is. Okay, so if I integrate here, maybe you want to pull out the 1/2 and just make your life a little bit easier. I got to carry my work up over here. So we got 25 halves out front. Integral of 1 du is just u, plus the integral of cosine 2u is sine 2u, but divide by 2. So that's what we have there. All right. To continue breaking this down, whoa, another double angle identity here. We don't use this substitution as often, but you'll see it come up with trig sub. What is sine of a double angle? It's 2 sine u cos u over 2. Okay, so now those 2's cancel. So we get 25 halves u plus sine u cos u. Okay, but wait, what is u and what is sine of u and cosine of u? We were doing this with respect to x at the very beginning. So what is u? Well, remember that sine of u is x over 5? What I know u is then, u is sine inverse of x over 5. So that's what I'm going to replace u with. From this relationship over here that we established with sine of u, u must be then sine inverse of x over 5. And then what's sine of u and cosine of u? Use your triangle right here. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So in the last and final step here, I'm going to say it's 25 halves u, which is sine inverse x over 5, plus sine of u is x over 5. Cosine of u from the right triangle, adjacent over hypotenuse, is radical 25 minus x squared over 5. Oh, and don't forget plus c. Okay, so it's kind of a crazy looking antiderivative in the end. I hope that you can appreciate all of the trig identities that got us there, and really that initial trig substitution, how it allowed us to create an integral that we could evaluate with respect to u. And this is something that, just like with anything, with more practice, you'll start recognizing when to use trig substitution. Again, it's really when you see integrals that involve something with a squared plus x squared, maybe a squared minus x squared within radicals like we have in this example. Okay, so although we could probably clean that up even just a little bit more, I'll leave that as our final answer for now. Okay, I'm kind of running out of space anyway. Okay, let's try another one. So on the next page, we have the integral of x squared over the square root of 4 minus x squared. When you see the square root as part of your integral, it is going to be a substitution with sine again. So let's set up the triangle that we're going to use for our trig sub here. And if this is the angle u, remember, if we're going to use sine, we want the opposite and hypotenuse to be, one of them to be x, and then the hypotenuse in this case, if this is a 4 minus x squared under the radical, that's going to have to be 2. And just double check that when you do Pythagorean theorem, that last missing side would be the square root of 4 minus x squared. So let's talk about some things that we're going to need to replace inside the current integrand here. So we know that sine of u is equal to x over 2, and therefore x is equal to 2 sine u. We know that dx is going to have to get replaced, so dx would be similar to what we did a moment ago, 2 cosine u du. And that should be good for now. I'm sure in the end I'm going to also need u once I eventually integrate here, but we'll see, and we'll wait on that for a second. Let's see if we can start making some substitutions. So on the top, that x is going to get replaced with 2 sine u. So it's going to be 2 sine u squared. The bottom, square root of 4 minus 2 sine u squared. And then, of course, dx, like we've determined here, is going to get replaced with 2 cosine u du. Okay, here we go. So the top is really 4 sine squared at this point. Underneath, let's see here, this is going to be 4 minus 4 sine squared. So if you factor out a 4, that's going to come out here as a 2. What's underneath the radical? 1 minus sine squared. Okay, so we're building from there. We got that 2 cos u d over here. So these 2's are going to cancel. Bring that 4 to the front. So we got 4 and then the integral of sine squared. And remember, this is really 1 minus sine squared is cosine squared. The square root of cosine squared is cosine. And look how nice that is. Okay, so with some trig identity substitutions, 1 minus sine squared is cosine squared. Square root brings you to cos. Cos and cos cancel. So we have now reduced this to 4 times the integral of sine squared u du. Okay, and really similarly to what we did a moment ago, you're going to use that double angle substitution for sine squared this time. Remember that that gets replaced with 1 minus cosine of 2u over 2 du. All right, so we can bring out the 1/2 here again to make that a 2 on the outside. And if we integrate 1 du, that's going to be u. And then minus the integral of cosine 2u is sine 2u, but over 2. All right. And then again, now we're at the point where we saw that double angle substitution before. Remember that this is really the same thing as 2 sine u cosine u, which makes those 2's cancel out. So we get 2 times u minus sine u cos u. And then last but not least, now we have to do some replacements with what these are in terms of x. So going back to the top, what is u really? Oh, okay, well, u is really sine inverse of x over 2. And we can determine what sine of u are and cosine of u are using our right triangle up at the top. So this becomes 2 times sine inverse of x over 2. Sine of u up at the top is going to be x over 2. Cosine of u is radical 4 minus x squared over 2. Don't forget about plus c. And then last but not least, you can certainly distribute that 2. And I didn't do it before, but I have like one more line of room left. So let's see, it would be 2 sine inverse of x over 2 minus, this is really a 4 down here. So times 2 is going to make it a 1/2 x out front of the radical 4 minus x squared plus c. Okay. So it's going to take some time. Okay, you have to be a little bit patient with the process here to look at something like this and recognize that trig sub is the best way to go. You might initially think maybe it's just a straight up u sub, but when you try and decide what your u equals, your du is not going to match up with anything else within the integrand there. Okay, so be patient with the process, but when you start seeing things like a squared minus x squared or a squared plus x squared, and you're not going to get sine inverse right away from it or tan inverse, then try and set up a triangle to determine what the integral is with some trig sub. All right, so if you want to try the last one, go for it. But otherwise, we'll do this one in class. Kind of like this one. Okay. So we'll save that one for class next time I see you. If you have any questions, of course, about things that we talked about in day 94 here, let me know. Otherwise, have a great rest of your day.